All right, electron configurations. This is something that you can kind of use the energy level diagrams that we've already done and use that kind of as your template for completing an electron configuration. So electron configurations show the arrangement of electrons, and it gives you the number of electrons and which orbital in which they are. And what you're going to do is you're going to list each subshell in order of increasing energy, with the lowest energy subshell always written first. What's our lowest energy subshell? 1s orbital, or 1s subshell. Add a superscript to each subshell to indicate how many electrons are in there, and then sum up the subscripts, or the sum of the subscripts is equal to the total number of, that's the sum of the superscripts. Superscripts is equal to the total number of electrons in an atom. So here's our energy level diagram for neon. Okay, this shows us we've got 2 electrons in the 1s, 2 in the 2s, and 6 in the 2p. So we've summed it up with this right here. 1s2, 1s, and then to indicate our subshell type, and then 2 to indicate with a superscript the number of electrons that are in there. 2s2, 2p6. If you add up those superscripts, you'd have 2 plus 2 plus 6 equals 10. And that's all there is to that. Okay, so then let's write the electron configuration for oxygen from its energy level diagram. Okay, so oxygen has 1s, and it's got 2 electrons there. It's got the 2s subshell. There's 2 electrons there. And then oxygen actually only has a total of 8 electrons. So after the 2s, we go to the 2p, and there are 4 electrons there. So our energy level diagram would look something like this. Up, down, up, down, up, 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 and then down. Okay, so our electron configuration, 1s2, 2s2, 2p4. All right. Now, electron configurations in the periodic table. The periodic table can serve as your guide for completing these electron configurations pretty easily. The elements in each group of the periodic table all have the same outermost electron configuration. So an example of that would be the configuration of the alkali metals, group 1, are always going to end with n, just an integer, 1 through 7, s to the first, or s1. Alkaline earth are going to be integer, n, s2. And the halogens are always going to have ns2, np5. These outermost or valence electrons give an element its chemical properties. Now, these valence electrons are going to become pretty important in a little bit when we start talking about bonding in the next chapter. The periodic table can be divided into blocks corresponding to the type of subshell occupied by the highest energy electrons. Here is that breakdown. We've got our S block, we've got our P block, the D block, and the F block right down there. Now, this is something that if you use this figure when you're working on electron configurations, you're going to help yourself out quite a bit. What we want to do is write out the complete electron configuration for an element like lead. Okay, now that's seemingly a pretty daunting task, but the way that we're going to do it is we're going to look at that figure. Now, what you can see here is lead is right there. It's in the 6th period of the P block. The second column of the P block, its highest energy electrons are in the 6p subshell, which contains 2 electrons. We're going to write that as 6p2. Now, everything leading up to that, well, this chunk right here, that is the 5d orbital, or a 5d subshell. So I'm going to write this backwards. 6s2, or 6p2, I'm sorry. 5d, there are 10 electrons that can go there. 6s2. Now you might be looking at that and saying, well, why 6s2 and 5d? Why is it 6, 5, 6? Well, remember that 5d subshell is exactly between the energy levels of the 6s and 6p orbital. Okay, or subshells. Next up is 5p6, 4d10. So what I want to do is I want to just go ahead and X through what I've written to kind of give me a little bit of guidance. Done, done. 5s2, done. 4p6, done. 3d10, 4s2. Now 3p6, right here, I'm done with those. 3s2, done with those. And then 2p6, 2s2. And finally, 1s2. That's it. That is the complete electron configuration for lead. Now, with all of that said, that's a lot to write. There's something that's known as your kind of condensed electron configuration. And for your condensed electron configuration, what you need to do is you need to find the nearest preceding noble gas. So for lead, the nearest preceding noble gas is right here. And it's not labeled there, but I'm going to label it. It's Xe, xenon. So what you do is you find the nearest preceding noble gas, and you bracket it. You say Xe. That's like saying use all of the electron configuration, the complete electron configuration for xenon, and then fill in everything that follows. So I'd write Xe, 6s2, 5d10, 6p2. Okay, I hope that was helpful. Now, the next thing that I want to use this same slide for, though, is I want to go ahead and think about ions. Now, when you think about ions, you think about the loss and gaining of an electron. Well, think about lead. Lead very commonly forms a 2+ ion. Okay, so what does that mean? That means it has more positive charges than negative charges. So in order for lead to form Pb2+, it had to lose 2 electrons. Now, if you were to look at that, okay, well, it loses 2 electrons. So what that means is that our electron configuration right here is going to change. And it's going to change and show that electrons have been lost. So what we do is we say, okay, well, where are those electrons going to be lost from? They're going to be lost from the most far out place that those electrons can be found. And where is that? For lead, it happens to be the 6p subshell. So I'm going to write the condensed electron configuration for the lead 2+ ion. It's going to be that same Xe, 6s2, 5d10. I don't write the 6p2. I don't write 6p because those 2 electrons in that 6p subshell have been lost. All right, so thinking about, well, that would be a positive ion form. What happens if you have a negative ion form? Well, a negative ion would be you'd gain electrons. So if you made the lead 2- ion, Pb2-, that would go from 6p2 to 6p4. All right. Now, I hope that's all been helpful, and I'm going to go ahead and stop right there. Those are the high points of electron configuration. One last thing, though, that I want to mention is this term. And this term is isoelectronic. Now, isoelectronic is when atoms and ions have the exact same electron configuration. So atoms and ions have same E config. So just as we saw here, Pb2 plus has the 6s orbital, these guys filled, and it's got this guy filled. So Pb2 plus is isoelectronic with this element right here. And that element happens to be Hg, or mercury. So Pb2 plus and Hg are isoelectronic with one another. All right, I hope that was all helpful. You got this, and we're almost done with chapter 8.